Okay, I'm going to try something a little bit different right now. This is the first time I've used this setup before, but what I'd like to do is to talk to you a little bit about a tool that I've found helpful for planning layout. And this tool is something I call LayoutDriven Schematics. And this is basically a way of making a schematic that plans how the layout is going to be. So it's kind of like doing the schematic in a way that has the layout kind of in mind. So normally we might have something like an AND gate. Let's say a two input NOR gate. Let's try that. So we might draw the schematic like this. There should be a bubble on that one. And a bubble on this one. And this will be our output Y. We have two inputs here, A and B. And then we've got our VDD connection up here. And so this is the way we would typically draw a schematic for a circuit like a two-input NOR gate. Well, this type of approach to making the layout, where we think about literally sort of drawing a transistor and another transistor and two transistors kind of in this spatial orientation, doesn't produce a very good layout. And so a layout-driven schematic is basically kind of warping the schematic in such a way that the placement of the transistors corresponds to the way we might place them in the layout. And this kind of goes according to the guidelines that we talked about in the last video segment. So for this kind of circuit, I might draw the layout-driven schematic as follows. We like to orient the transistors horizontally. And so I might take my two PMOS transistors and draw them like this. And my two NMOS transistors I might draw like this. And then my output, the output of my gate is going to be over here. Z, actually no, it was Y. Like so. And then this is, let's say, my A input. And this is my B input. And now I have to make my, actually no, this is going to be connected, the output of the gate is going to be connected, let's say, right here, like that. And now I have to connect up the power supply, and I would connect up my VDD here. And I might connect up my ground here and there. Okay, so you remember the way that we had our, the way we talked about organizing the digital layout was so that the transistors kind of ran in strips, like the diffusions or the active regions ran horizontally in strips parallel to, let's say, a VDD rail, which you could imagine extending this little symbol out here and a ground rail down here. And so we can tap off or tie up to the VDD rail where we need to. We can tap off to the ground rail where we need to. And then we have our transistors with the gates coming across, and this would be the polysilicon coming across like this. And we basically order the transistors in the order that they would appear in the layout, and we would align vertically here the transistors that correspond to each other in the pull-up and the pull-down network. And so you can see that the connectivity is the same here as it is over here, but this actually will map very nicely onto the layout. And so when I have to plan a layout, I don't typically think about doing Euler paths and logic graphs like I had in the video. I tend to do something like this. I tend to get near a whiteboard and grab a dry erase marker and take the schematic that might have been prepared like this and try some different possibilities out. You know, I might start out with the transistor rows like this, and then I might play around a little bit with different possibilities for the connections. Like, for instance, you know, we could think about the option where we have something like the ground tapped off in the middle, which is something more close to what I started to draw, like that, and then have this tied here, and then have this come over here like that. But of course that doesn't seem like that's going to be a great idea, because we're putting more capacitance on the output node from this drain and this drain than if we tap it off in the middle and we don't have ground on the outside of the cell, so that it might be able to be shared with or merged with, let's say, a ground substrate contact on either end, or maybe share a ground tie with an adjacent logic gate or something like that. Okay, so this one I wouldn't think is as good as, or preferable to, the one I started with here, where I guess I need to erase this one like so, and then we make the connection up to the output like that. And actually, when I'm creating a schematic for doing layout versus schematic, which we'll talk about in a tutorial a little bit later, and it's going to be part of your first mini project, I would tend to actually make my schematic for LVS purposes, if not for simulation purposes, in this format before I start doing the layout, as a planning tool for actually doing the layout. So this is one example. This is a 2-input NOR gate. If we were interested, we could try a slightly more complicated gate. Oh, suppose we had a gate where the pull-up network looked like one transistor here in series with 2 transistors that are connected in parallel with each other, let's say. And so if we wanted to, we could synthesize. So this is our output Y. And we could call this, let's say, A, B, and C. And then to synthesize the pull-down network, we've got 2 things in series. And so that will correspond to 2 things in parallel. And probably don't need that dot there. So the 2 things in parallel are going to be a single transistor, which is A, and then the other thing in parallel is going to be a branch with 2 transistors in series. This is B. And C. And so this is a random gate that I just made up. It's not a standard gate, obviously, and it would be Y would equal, let's see, it would be A or B, C bar. Right, so that's reading off the logic function for Y bar from the conduction condition for the pull-down network. Okay, so we have A in parallel with B in series with C, and so that corresponds to A or B, C, and then we invert that for getting the getting Y bar. So that's what this gate implements. And so to do the layout-driven schematic, I might start with, well, I don't know, something like my VDD connection, like that. And I might have an A transistor. Now I've got a B in parallel with C. Okay, so there might be a B transistor next, followed by a C transistor. And so we'll make the A, B, and C transistors for the pull-down network aligned underneath them. Looks like I'm kind of going off the edge here a little bit. So let's try getting these a little closer together. And then see if we can get these more or less aligned underneath here. Like so. So we said this was A, B, and C. And now, let's see, we're going to have B and C in series with A at the output. So this is going to be our ground tie. And we're going to have to make a jumper over here. This will be the output. Y. And then to do the pull-up network, B and C need to be connected in parallel. And to do that, we're going to connect the output of the gate here. And we can jumper this over here. Okay, so that would be a way of doing the layout-driven schematic for this gate. So here we come down from VDD, we go through the A transistor for the pull-up network, and then we have a pathway through B, and then through this jumper over here, a pathway through C to get to the output of the gate, which is over here. And then for the pull-down network, we have A connected to the output of the gate, and that appears in parallel with B and C in series connected to the output of the gate. And sometimes you don't get the right ordering to begin with, and sometimes you're not really satisfied with the way these connections have worked out. And so you might just, on the dry erase board, you can basically just erase something and try something out very quickly. And so I found that this is a very good way of planning layout in my experience. Some people use something they call stick diagrams, which is kind of like a cartoon layout where they don't actually use rectangles of any actual physical width. It's just a matter of like drawing kind of like sticks. So you draw a line that represents the diffusion or the active region. You draw a line that's vertical here that represents the polysilicon, but they're just like thin lines. You might use colored pens or pencils or something like that, or dry erase markers of different colors. I personally find this sort of quasi-schematic representation where we're not really concerned with, how wide this is going to be physically at this point. We're just concerned with kind of the relative positions of the transistors in space. But there's some more notion of space over here that maps onto physical space than there would be in the schematic, where we tend to arrange things so that higher potentials are higher up on the page and lower potentials are lower down on the page. And there's usually some sort of progression of signal flow in the schematic from left to right instead of, some other direction. And so here, the inputs, you could think of them as coming in from the bottom, or maybe coming in from the top, or some mixture of the bottom and the top. And then the gate's output might be available over here at the right, or it could also be routed on a vertical channel here as well. So the name Layout-Driven Schematics is one that I sort of took from something that's popular in some CAD tools, especially for doing things like mixed signal layout or analog layout, where you've got a schematic and these transistors are just gargantuan. They are very high W over L transistors, and what will happen is you draw on the schematic, and the automated layout tool, which is supposed to be a big help, basically will take this transistor and stack it. So it cuts it up into little strips and creates a block, which is representative of that transistor. And it plops it down in a physical position that's correlated to where it is in the schematic. And then you take your automated generated transistor blocks, and then you wire them up with metal wires. And that's not really a great idea, because the way that you lay things out in the schematic view has to do more with the way you make things intelligible to humans who are looking at your documentation, not how they might be better represented on a physical connection, where in a layout, or in a schematic rather, we might connect things through just net labels, and so there doesn't have to be physical proximity in order to make the wires short. Whereas in this kind of view, where it's more oriented toward the physical design of the system, we like to put things sort of near each other so we can optimize the way wires run and things like that. So you notice I've got the A and the B here connected through a wire, and it's a short wire, as opposed to here where, if I wanted to connect the A and the A, I'd have to kind of go over here and jump over the B or something like that. But when we get to analog layout, we'll find that one of the things about matching is that you often will take transistors that are supposed to match each other, like in a differential pair or like in a current mirror, and you will break them up into strips, but the best matching is achieved by interdigitating those strips so that each corresponding subunit of the transistor will be physically close together, and you can take advantage of local correlations between different transistors. And so that will match better those two devices than if I have the A device and the B device kind of next to each other like this, and not physically kind of interleaved with each other. And so these so-called schematic-driven layout tools don't typically produce very good layout at the end of the day. But if you do the schematic with the layout in mind, you'll achieve much better results. And I use this both for digital gates that I have to design, and also for doing analog cells that I have to design. And so we'll see some more examples of this, both for digital and for analog cells as we go along. So this is meant to be sort of a quick video, and hopefully it makes sense. So talk to you later.